Okay. Uh, anyway, uh, uh, the uh, well, uh, another mess up on my behalf. I've forgotten to turn on the recording. So this is a brief synopsis of what happened before before I did turn off the recording. Anyway, we need to prove that the code was finite dimensional. Let's do that. So we um, uh, then we have the kernel A, no, the kernel B plus the kernel B orthogonal, and this this is P. Why? Because we just proved that the kernel is actually no. This is true in general because the kernel is always closed. So we have this identity for all for every operator. Now, now let's see what happens when we apply B. Uh, well, the kernel goes to zero. And the orthogonal complement goes to uh, the image of B, which is dense in the orthogonal complement of the cardinal of B star. Okay, uh, this thing is inside the kernel of B star, and moreover, it's dense. And then we have with this decomposition. Now the let's see. Now what is the operator B star? Uh, B star is the identity minus A star. And this operator is also compact. Sorry, the joint of the compact operator is compact. Now let's let's see. Let's see where this is going. Um, I want to prove that um, uh, sorry, there's something. No, no, there's something. The image of B. Yes, the orthogonal complement is at the wrong place. Okay, now this is better. Now, if I prove that the image of B is not just dense but coincides with the orthogonal complement, then then uh, 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 then the proof is finished because the kernel of B star is finite dimensional by what we already proved. So uh, if the kernel of B is exactly equal, if the image of B is exactly equal to the kernel of B star orthogonal, then we're done. Uh, okay, so I have constructed this diagram, but there's it works in the same way uh, uh, for B star as well. So the kernel under the map B star uh, um, uh, the orthogonal complement of the kernel of B star goes to the orthogonal complement of the kernel of B. And again, the image is dense, but we don't know yet that the image is the whole thing. Now uh, let's see what happens. So um, let's apply B first and then B star. No, no, this is not it. Let's apply B first and then B star. Uh, and let's restrict this to the kernel of B orthogonal. And the result is, well, I minus B, I minus B star, I minus B, which is I minus, sorry, I minus A star. Uh, which is I minus C, where C is compact. What is C? Well, C is minus A star minus A minus plus A star, and we basically use the fact that compact operators form a two-sided ideal in the space of all operators, which is not very hard to prove from the definition. And such an operator is invertible. Let's assume this for a minute. Such an operator is invertible, so we have uh, uh, two operators. We have the operator B going from the kernel of B to the kernel of from the kernel of B orthogonal to the kernel of B star orthogonal, and we have the operator B star going in the opposite direction. So both compositions are invertible. So both operators are themselves invertible. Yeah, does this part make sense? Saman, why is it true that if I have two operators between two Hilbert spaces, well, let's call this V1 from V1 to V2, and V2 from if V1 composed with V2 and V2 composed with V1 are invertible. So are V1 and V2. Someone, why is it true?
Um, I guess if, for example, one of them is not invertible, for example, if B1 is an invertible, it might have a kernel or it's not surjective. So, for example, if it has kernel, so B2 composition with B1 is not invertible and vice versa. We can have the
Well,
contradiction
okay,
this way.
yes, yeah, it makes sense. So uh, both operators have uh, zero kernel and uh, 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 are surjective. What does this mean? Well, this means they are invertible as operators. They are invertible as uh, in the sense of linear algebra. And using the Banach open mapping theorem, we deduce that the inverse operators are in fact continuous as operators from as operators between Hilbert space. Okay, so the kernel both these operators which are written here uh, are in fact invertible. Well, does this uh, does this finish the proof? Well, let's see. Leonid, what do you think?
So we wrote that this B and B star are invertible, right?
Well, they are invertible when restricted to the kernel of B orthogonal and the kernel of B star orthogonal. And recall that we want to prove that what do we want to prove? Uh, we want to prove that the image of B is not just dense; it's exactly equal the kernel of B star orthogonal. Well, since the map B is an isomorphism between the kernel of B the kernel of B orthogonal and the kernel of B star orthogonal, uh, um, we we have this equality. So let's put this down. Okay. Uh, okay, so there remains to prove there remains one thing we didn't prove identity minus or plus a compact operator is invertible. Does anyone have an idea of how to prove this? Vladimir, how do we prove that the identity minus a compact operator is invertible where V is a Hilbert space? Vladimir, what do you think? Okay, can anyone help? Well, what's the idea? How can we find an inverse operator? Leonid, what's the first thing that comes to mind when we want to invert some identity minus something?
Use series I plus C squared plus so on.
Exactly. Yes, we use the geometric progression. So I plus C plus C squared plus etc. But we need to show that the series converges. Well, normally one would want to use the norm, but this doesn't really work because the norm of a compact operator might well be 1 or 2. So the series of the norms may not converge. So what do we do? Okay, I don't remember this part. If uh, if no one else if no one else has any ideas on how to handle it, let's see. Let's say it's something for us all to think about at some later point.
I guess there was a condition equivalent to compactness with eigenvalues, so maybe we can use that. I mean, we can use them as triangular operators. And so when, for example, C squared, and I mean, they have eigenvalues, we should,
Yes,
I guess they must be Cauchy or something.
Yes, well, there's so compact operators have the spectrum of a compact operator cannot be arbitrary. It has just one accumulation point, which is zero, and some number of other points, and all other points are eigenvalues. But I think there's a simple way to prove this. I just don't remember. Okay.
I think this fact is not true even in finite dimensional case.
Well, yes. So let's see. So in the finite dimensional case, all operators are compact. Yes. So yes, and on the other hand, not all operators are invertible, which is which is an inconvenience. Let's see.
Maybe it's not true when dimension is finite, but if dimension is infinite, then it is true.
Well,
I don't know.
well, it's almost true. Meaning there are complementary subspaces of. It's true modular finite dimensional subspaces, which means there are complementary subspaces on which this operator is invertible. But this is what we're trying to prove. So it's not exactly it's not exactly a valid trick to use. Let's see. Okay, so before the time runs out, let's just say that this is wrong in general. This is an assumption that we make. Just compactness is not enough. Okay, let's erase this because this is it's not it's not true in this generality. Okay, so there is Okay, let's get rid of this this pod. Okay, let's okay, let's save the notes. Otherwise, they'll just vanish. Okay. I need to think some more about this argument. And I think the operator will turn out to be invertible. But we need some more argument to prove this. Okay, I've saved the notes. Let's reconnect again in a minute and discuss what we do next.